All right. Hello, folks. It is Monday after Easter. Hope everybody has enjoyed their Easter celebrations or Hanukkah. No, it's wrong. Passover, wrong holiday, or whatever you're celebrating. Even if it was just celebrating having an extended weekend with your family. All right. Anyways, where we are is we are going to be finishing off confidence intervals essentially today. And, these are going to be some of the more complicated sections of confidence intervals that I believe in your book is chapter 8. Okay. And we will probably finish that off today and then start the concept of hypothesis testing next. So what I want to do is create a test on any and everything confidence intervals, which would be a week from today. So a little bit of a heads up warning. Week from today would be our next test, and I'll talk a little bit about that probably on Wednesday. All right. Before we get started, any comments, questions you have, anything like that? I did have one comment or an email. I don't know whether whether that applied to this class or not. Normally I have my homeworks due on midnight, and I guess I had screwed that up for one of the classes, and I have to go back in and see which one that is. But anyways, there is no penalty for doing homeworks late. So if you want to get homeworks done and you are worried about them being late, don't worry about them, just submit them. All right. All right. We were looking at confidence intervals, and the things that we are looking at right now are differences between means. All right. So one of the things that where I call these left Twix, right Twix problems, and that may make sense for those of you who watch TV and see the right Twix, left Twix TV commercials. For those of you who never watch TV, good for you. And essentially, we're trying to see if there is any difference between two populations, or how much of a difference there is. Right? A series of really good examples on this. Okay, are cases where we're looking at two machines to see if one or two more of them is broken, right? I've got a motor that I'm not really sure has as much horsepower as a new one, or battery life difference. Okay, how much more battery life is there in a 1-year-old computer than a 3-year-old computer, right? Those types of differences come up relatively frequently. The example I used with the school teachers, right? School teachers, third grade teachers, get a whole fresh set of second graders given to them at the beginning of the school year. And at the end of the school year, they supply the principal a set of students that have gone through a year's worth of instruction, right? We would hope that during that year that the teacher had these students, that their reading comprehension would have gone up, that their math ability would have gone up, that their sense of history and social studies had gone up, that their science, whatever they're studying in science, had gone up, right? And we may want to be measuring how much third grade teachers have influenced their children, right? So we may be taking a sample of third grade students at the end of the year and take a sample of third grade students as they enter the year and ask the question, what does the school district do in terms of adding value, right? We frequently got pre and post tests, right? I think we have stopped doing that, but it used to be that that most of the general ed classes here at Texas A&M Kingsville had as a measure pre-tests and post-tests. And the idea here was let's measure how much value added these classes had. We didn't really want to punish teachers for having had students who come in at a slightly lower level, and we didn't want to reward professors for getting the luck of the draw and getting students who may have had all of this in an AP class in high school, right? So essentially what was done was we took a pretest of students' ability before the class, and we took one after the class, and we kind of looked at those and tried to figure out, did the professor actually teach anything, right? So we can think of business examples after business examples after business examples where what we are interested in are comparisons between two groups, okay? We may want to look at the comparison group between female students and male students to figure out, okay, how much better are the female students in English or some other subject matter, biology, versus the men, right? We may not have any idea, and honestly, I don't have a freaking clue as to what the abilities of female javelina versus male javelina or in terms of their biology knowledge. Okay, that would be something that would be of interest to me. I don't think I have a need to know, but it's be something actually I'd be interested in. Is there a difference? I assume the answer is yeah, there is going to be a difference, but in which direction and how much? These are things I don't know. And if I were president of the university, I might want to know, right? Okay. And so what do? I will go out and take samples, right? And that's where we kind of left it last time. Right? And when we are doing these comparisons, we will have to take two samples, right? And so we have two groups that we are interested in, group 1, group 2. Okay, let's say this is male and this is female. And let us look at the biology MFT scores. I don't know what MFT stands for, but it's some standardized tests, right? And if we were to give all of the males, okay, a test, which we don't really have the budget for, right? But if we were to give every male student on campus a test that measured their abilities in terms of biologies, some kind of score, right? There would be a mean, there would be an average from the first group or the male group. The mu of the males, right? This is something we don't really know. Similarly, the females, their knowledge is unknown, right? And what are we looking at? What we really wanted to know is how much better are the women versus the men? So what we want to know is mu female minus mu male equals mu difference. Right? So as we're trying to estimate that, mu is what God knows. Okay? Since we believe in Greek gods in this class, we believe that the Greek gods know everything. And the Greek gods know this stuff before they actually make the guys take their tests, because they know what the guys would get if they were to take the test. This is the ever-knowing God theory of statistics, right? You don't have to learn statistics if God speaks to you, right? Because all you're trying to do is figure out what this difference is. So we're trying to look at the difference of the females versus minus the difference of the males, and that gives us our mu difference, right? And this is what we wanted to know. On average, how much better are the women than the men? Right? Positive number would mean that they are that much better. A negative number would actually mean what? Negative number would mean that the males are better than the females, right? 0 would be that there's no difference, right? We don't know that, okay? So what we're going to need to do is to take a sample from each group. So from this sample, we will take a sample of female students, and normally what we will have is 1 and 2 for group 1 and group 2, because male and female writing those out become difficult, especially if you are somebody like me who can't spell very well, or someone like me who writes something almost unlegibly like this, which should say difference, right? So what we want to get from the first group, the male group, oh, this first one was the male group, sorry about that. Okay, was we wanted to get the X bar. We wanted to get how many did we sample from here? N, right? If we needed it, if sigma is known, we don't need it, but if sigma isn't known, we need to calculate what S is, sample standard deviation, because we're going to go and use that over here, right? So to find the difference, we're going to need to take a sample of the first, and we're going to take a sample of the second, a random sample in both cases. So this would be X bar female. There's an N for female, right? If sigma is known, great. If not, we're going to have to take. Okay. If sigma is known, great. Okay. If not, we're going to have to take the sample standard deviation as our estimate from this. Okay. And so what we ended up with was a formula for our best estimate. Well, what is our best estimate of what? This. Our best estimate of the real difference that God knows, but we're trying to find out from taking our samples, right, is our best estimate of males and females is we plug in X bar female for mu of female. That's our best estimate here. This would be our best estimate of that. The best estimate of the difference would be the two subtracted from each other, right? And that gives us our X bar of the difference, which is this would be our estimate for that, for the mu, right? And so what we had done last time was what we did was we computed the formula, okay? And I'll let you guys look at this for 1 second before I erase it all and start writing the formula. Remember, our best estimate of the difference is this, right? So we're going to start with that. We're going to put that on the bottom, back. That's our best estimate. What is the probability we got that best estimate? Perfect. 0. Probability that this is a perfect estimate for mu, male, is 0. Probability that this was the perfect estimate of the female's ability is 0, right? Probability that we got both of those right is like double 0. We know that we didn't get it exactly because we just took a sample, right? So what we needed to do is figure out how much padding to put on both sides. These formulas look the same as we were looking at before, all right? So what does that formula look like? Okay, plus or minus, and I wish I put this sideways so I have more room. You know what, I'm going to put it sideways so I have more room. To make more room, I'm just doing F and M's. X or F minus X or M. Okay. This is our best estimate of the real difference. Plus or minus Z, just like we did it before, right? And then the formula got a little bit more screwy. Let me see if I can get the appropriate formula here from the equation. And that formula is formula 8.7 on page 289. And it is x bar female minus x bar male plus or minus z times the square root of sigma 1 squared over n1. And in this case, 1 was female, right? Plus sigma squared male over n male. We're just doing this. And your book has 1 and 2, group 1, group 2, right? Remember that subscript is just to let us know which X bar we're looking at because we're looking at more than one, right? Or which sigma we're looking at. You know, superscript, that's squaring, that's real math. The stuff down on the bottom is just a notation for, well, which one of these are that we're looking at, because we're looking at more than one, right? So this is the formula that we would typically use, right? And if sigma is known, we can compute it. If sigma in each case is known, we can compute it, right? Now, if sigmas are not known, but n1 is large or n2 is large, what are we going to do? We're going to just replace the sigma with s, right? And then we're just going to pretend like everything is hunky-dory. which we can do when n1 is larger than 30 and n2 is greater than 30. If that's the case, right, what did we do before when we were just doing one confidence interval? That second formula, just replaced the sigma with an S. And if n was large, it said, hey, don't worry about it. It's okay, right? Now, what happens when we have to substitute, okay, an S for it, right? And so let me find the right formulation for it. Okay. And let me see if I can find the right formula. And pool. Anyways, what we would end up doing is replacing this, and we would replace this with a t distribution. Okay, let me see if I can find the difference between two populations. Let me make sure I get this formula exactly right. Actually, I'm looking to see if your book actually has it. Your book says, okay, we are not going to be worrying about this, except for the scenario that we use the pooling. Okay. Okay, your book doesn't actually go through the formula when n is less than 30 or greater than 30, with the exception of a scenario where we are going to make a claim that S1, that the sigma for the first group and the sigma of the second group are the same, right? Okay. And at that point, okay, we are going to replace the sigma with an S squared. Okay. Okay. Under but if we believe, right, and this is the case that your book goes through, and we're not going to go beyond what your book does, okay? Your book says if you don't know what SF and SM is, right, what we can do, but if you know that the sigmas are the same, if we believe that the sigma of one group and the sigma of the other group should be the same, we have reason to believe that, we can go into our sample. Our S1 would be the sample standard deviation from the first case, right? The second one would be from the second case. And what we end up with is getting two different estimates. Neither one of them is particularly good if our n's are small. So if we believe they're the same, what we may want to do is pool our estimate and say, well, we got some information on S from looking at the first sample, and we got a different estimate from S, a different estimate S for sigma, because S's are estimates for sigma. From the second one, if we combine them, we should have an even better average. We would have a better guess as to what sigma really is. And if sigma is the same in both populations, okay, what we want to do is get our best estimate for sigma, and that would be pooled. Okay, and let me see what the comment was. Is this a t here? Yeah, we're going to be using a t distribution, right? And so what we end up with, okay, is, let's see where we end up with, is formula um, 8.9 and 8.8 on page 291 in your book. Page page 291. So, in order to get our best estimate, okay, what we are essentially going to do, our best estimate for sigmas, which is from our pooled combined data, is n minus 1 times S1 squared plus n, this is n1, n2 minus 1 S2 squared, all over n plus 1, n1 plus n2 minus 2. So in a weird type of a scenario, this pooled, and then we take the square root of this S pooled is essentially a weighted average of our first sample and our second sample, and we weight them not by how many observations n there were, but we remember that first observation in each group was worthless. So we multiply it by n minus 1 in both cases. So this would be our first sample minus the n from our first sample minus 1 times S1 squared plus n2 minus 1 times that, all over n1 plus n2 minus 2, okay, as a denominator, and then we take the square root of the whole thing. So this becomes somewhat of a complicated formula, but we end up with a formula that looks like this. What I was missing was, this is our best estimate plus or minus t times the pooled. Okay? And the pooled ones we calculated from here. You can't see. Okay, this is why I should look at it. The difference, plus or minus t times this, right, is the pooled, and this is 8.9 is the formula in your book, and this is formula 8.8. Now, when we go to the t table, remember degrees of freedom. When we were doing a simple study, okay, our degrees of freedom column was what? It was n minus 1. Why? Because we lost a degree of freedom when we were calculating the differences of each sample. In this case, we are taking 2 samples. Each time we are losing 1 degree of freedom, okay? because the first observation from the males does not help us at all in estimating S's, right? When we went to the second sample for the females, the first observation of the females gave us no information about how different the females were, right? So we lost a degree of freedom there. Okay. So when we use the t-distribution in this case, we will end up, when it comes down to figuring out what row we're at, what degrees of freedom, okay, we're going to have N1 plus N2 minus 2, and that will give us our degrees of freedom line. Okay, and then we can look that up in the table. Okay, so these are relatively complicated scenarios. Okay, they're not that complicated, but when you want to do them, you're probably going to go back to the book and you're going to learn how to do this. Right? So let me step back for a few seconds and just talk about what we just did. We took a random sample of group 1 and a random sample of group 2. Right? Now, when we took a random sample of the men, it is possible just by randomness that we picked some of the smartest men on campus purely by random. Right? When we went to pick the women, we may have by complete accident picked some of the not so smartest women on campus. If that happened, which it does happen, right, we would be quite off in our estimate, purely by chance, right? Which is why it was important to understand how much different people were, right? But there is one case here that we might be able to do a better job. And this is one of those instances where having a little bit more knowledge of the situation, okay, and what we're trying to accomplish can reduce some of the variability. And as we reduce the variability, we are getting a better estimate, right? Now, let us go back to the pre-test and post-test, right? If I just take a random sample, okay, of men and random sample of women, I might run into the scenario that in one group I get all the smart people and all the not so smart group when I did another random sample. If we are doing something that we can pair, okay, let's say we take our third grade example. If I take a sample and I am able to pair a particular student with a post-test and a pre-test, right? Now, I don't have an issue that I might have accidentally had a smart person randomly at the end versus a not so smart person in the beginning, right? Because we have the same pairs, the same individuals. So we are taking away some of that confusion, right? So this works when you can take a pre-test and a post-test of the same individual, right? And we call that paired sampling. Okay, we pair them off because we know fundamentally if we did that, we can remove some of the difference. We know if this particular student did well on the post-test, but did poorly on the pre-test, that the difference is because of what the teacher taught. Right? So in that particular case, we're going to do things completely different. Okay? In that particular case, what we are going to do is have a student ID. Student 1, 2, 3, 4, 5, 6, 7, all the way down to the last one, right? And then here, this would be the X after. And this would be the X before. And this would be the X difference, right? And if this first student was at a reading level of 3.3 at the end, we started at 3.1, 0.2 would be the difference between them. This student ended the year at 5.3, started at 2.1. They increased 3.2 levels, right? This third student, okay, let's say 2.5, 3.5, grew 1 grade level. This student started at 3.0, ended at 3.0, and had absolutely no growth, right? 3.1, 3.9, 0.8, and so on and so forth. And what we end up with is 10 students, and for each of those students, we have 1 score, which is how much they improved. And then, in this case, we can just take this column of how much they improved, right? And treat that as 1 variable, just like we did before in the beginning sections, right? And our estimate of how much our teacher has improved would be from this sample where we got both before and after of the same student. We get the difference. And what is our N? We have 10 observations of the differences. And we can reduce some of the variability this way, okay? And because we reduce the variability, we are improving our estimates, okay? So when you have this type of an environment where you can do pre-test and post-test on the same subject, okay, it's sometimes useful to tie those two together. But that generally means you have to do them at 2 separate times. Whereas this, going the other route, okay, has other advantages because we can look at students coming out of 3rd grade, and we can look at students coming into 3rd grade, and we don't have to wait for those students to come into 3rd grade to leave 3rd grade, right? You just want to know these differences. Right? The other reason why this paired solution may not be that great is after you're taking the pre-test, you would have to tell people, oh, by the way, I'm going to take your name because I want to pair you again with the post-test score. So I want to get your name both times so I can match them. Right? And some of your students may say, oh, this isn't going to end up well for me. What if I'm this student here? I start out 3rd grade reading level, I end up with 3rd grade reading level. You want me to do these statistical tests for you? I think this is going to come back to bite me. You are not going to treat me anonymously. You're going to say, oh, he didn't learn anything in 3rd grade. I think I'm going to flunk them, right? So there's a anonymity problem if you're doing a sample like this, where you're doing pre and post and you're merging them together. That your students or your selective, whatever you're studying, may not want their names associated with it. The other way around, you don't have to collect their names, right? You can let them know, I don't need any personal identifying features of you. And you're going to get potentially more people who are interested in helping you be a student in this type of environment. Okay. Now, what we covered today, okay, this is on the advanced side, okay? I'm probably not going to have an awful lot, if anything, of this on the test. I am more than happy. Well, let me step back. I may have a simple question or two, but I'm not going to make you do a big exercise doing it, because the formulas are screwy, they're messy. There's a high probability somebody makes arithmetic mistakes and so on and so forth. So I may have a couple multiple choice questions to make sure you understood the concept of what we were trying to do, right? So as you're reading that on the comparing the means scenario, read it, try to understand it. Don't expect that I'm going to make you be able to do this on a test, okay? I know it's open book, but even in an open book test, I'm not going to make you do it, all right? But still, there might be some multiple choice question or two regarding this chapter, understanding the concept of why you're doing things the way you're doing it. Does that make sense? All right. With that, I'm going to call it quits for the day. Are there any questions? All right. Where I'm going to start, where we're going on Wednesday and Friday, okay, is we are going to go to hypothesis testing. All right. Hypothesis testing is going to be its own little section. We're going to have a whole series of formulas. We can do a little bit of the hypothesis testing here. When we developed a confidence interval, there are some things that the confidence interval will let us answer that are hypothesis testing type questions, right? But we're going to have a whole different set of formulas that are very specific to hypothesis testing specifically. What is the difference? Well, up until now, we did not know what reality was. And our boss wanted us to find out what our best guess is what reality is, right? Now, we knew that our best guess is just our best guess, and we need to figure out how much padding to put on both sides. Even when we went to those formulas that we did today, the ones that are really complicated, they're still the same thing. The differences from our sample, plus and minus the stuff in the back. And the stuff in the back talks about how much padding we're putting on both sides, right? So those are the types of things that we're doing. In hypothesis testing, basically our boss does not come and say, you know what, I don't know what reality is. Please estimate what reality is and give me a clue, right? That's what we just did. In hypothesis testing, the boss will say, I know, or I am pretty sure I know what reality is. And I'm going to go with that. But can you just do some data and make sure that I'm not saying something stupid, right? I'm pretty sure I know what reality is, okay? But go look at a sample and verify that what I'm saying is not completely contradicted by the data, because if I find out that really is, then what I'm saying is just going to embarrass me as people find out that I don't know what I'm talking about. Right? That is the next section of the class. That's called hypothesis testing. All right. With that, I'm going to call it quits for the day. Any other comments? Any questions? All right. We're all done.